So in chemistry, a closed system, can somebody say what it is again?
No chemical substance can escape the container, and I forgot the rest.
Okay. So just to repeat for the sake of the video, in physics we talk about isolated systems. You are familiar with that.
Yes.
But in chemistry you can't talk about an isolated system, you talk about a closed system. The second thing, what is a reversible reaction? In grade 10, we taught you that it is difficult to reverse reactions. Some reactions you can't reverse. Some reactions will reverse with ease. Okay? So what is a reversible?
Something that can undo itself.
A reversible reaction, yes?
It's not a reaction where the product of reactions can become reactions.
Yes.
Formed.
Yes. The products that are formed by the reaction will revert back into the reactants that formed those products. So a reversible reaction is a reaction where the products formed during the reaction can revert back into reactants. What does your exam guideline say?
A reaction is reversible when a product can become breakable back to reactants and vice versa.
Okay, so I was right. And vice versa it says. Okay, the third thing I want to say. If you have a reversible reaction that takes place in a closed system and the temperature of the container is kept constant, you can have, in the end, a dynamic chemical equilibrium.
What do you mean by dynamic?
I'll talk just now. Okay. So in a closed system, dynamic means the reaction will never stop. Chemical equilibrium will mean that the rate of the forward reaction equals the rate of the reverse reaction. So dynamic means the reaction will never stop. And chemical equilibrium means the rate of the forward reaction will equal the rate of the reverse reaction. The example I'm going to use is the Haber-Bosch process. It is an industrial process. Good afternoon. Okay. The Haber-Bosch process is an industrial process that is used to fixate hydrogen and nitrogen. It makes it available in the form of ammonia, which is an essential component in fertilizers because the nitrogen is needed to make protein. The ratio is okay. A reversible reaction is indicated by a double arrow like that. The nature of the reaction is indicated by the change in enthalpy, the delta H. The forward reaction is from left to right, and that is an exothermic reaction. The forward reaction is the exothermic reaction. So the forward reaction is the from left to right reaction. You're keeping up?
Yes.
Okay.
Are you saying that this is dynamic like the point of this the point of you showing us the Haber-Bosch process is it to say that it's are you trying to show us like the dynamic chemical equilibrium?
Yeah. Okay. I'm trying to explain things. Let's say we start off with 6 molecules of hydrogen. How many nitrogens would I need?
We need 3. Nitrogen, we need 2.
2 nitrogens. Okay. The ratio is 3 to 1. Okay. How much ammonia will there be in the container?
2.
Initially, at the start.
Oh, 0.
At the start, we will have no ammonia. So what can you tell me about the rate of the reaction at the start?
It's going to be 0.
The rate of reaction.
You put the nitrogen and the hydrogen into the container. You have a high concentration of reactants in the container.
Very quick.
You start off with a high rate of reaction. And as the nitrogen and the hydrogen reacts, the rate of the reaction slows down. Okay? So initially you will have a high rate of forward reaction. Okay. After, so let's let's say one of these nitrogen molecules has broken up. How many ammonia molecules will form? Yeah, one molecule breaks up. How many ammonia molecules will form?
One.
Hi, Werner.
3.
Hi, Werner.
2.
One nitrogen, 3, 4, 1.
There will be 2 ammonias.
Oh, yeah.
So what's happening as the reaction takes place, more ammonia forms. Am I right? But the more ammonia forms, the more it will break up into nitrogen and hydrogen again. It's a reversible reaction. So the more ammonias form, the more they will break up into hydrogen and nitrogen again. So there will be a high rate of a forward reaction. The amount of NH3 will increase. So my NH3s has increased now to 2. And what happens to them then? They break up to make hydrogen and nitrogen. So if one of them broke off, 1, 2, 3, 4, 5, 6, so 3 molecules of hydrogen will still be there, and 1 molecule of ammonia, 3 molecules of hydrogen will be there, and 1 molecule of nitrogen. Say this molecule breaks up now. Say this molecule breaks up. It will take 3 more of the hydrogen molecules. Am I right?
Yes.
Aye, but in the same time, what happens? In the same time that those 2 molecules form, these ones will break up to make another nitrogen and 3 more hydrogens.
So does it ever stop?
No, it will never stop because it's a dynamic chemical equilibrium.
Ma'am, please run through
Pardon?
it. Please
Please?
run through it.
Okay. So, initially you have hydrogen and nitrogen. They react to form ammonia. Let's say one of the nitrogens break up to form 2 ammonias. 3 of the hydrogens will break up to help form with the ammonia. Are you with me? But who says the next nitrogen can't break up? So if a nitrogen breaks up, it forms 2 separate atoms which will react with the hydrogens that are in the container. So these hydrogens, they break up to make the bonds with those 2 ammonia. But at the same time, these ammonias will break up to form to form nitrogen and 3 hydrogens.
Wait, ma'am. My question is, where do those two nitrogens come from for them to have bonded with the hydrogens? The ones from that side, from in the end. What you just said that they break up. Like, where do they come from? That's what I'm
It's a
confused.
spontaneous reaction. This
No,
reaction.
ma'am.
They break up.
How did
Okay.
they break up? Like, they were together. There was there were two ammonias. So then, all of a sudden now, where did the two nitrogens come from? That's what I'm asking.
Okay. I'm using a hypothetical reaction. Here I've got a ratio of 2 nitrogens and 6 hydrogens. They are going to react, the bonds break up, and they make, let's say, only one of the nitrogens break up. But they won't stay broken up. That's the nitrogen that breaks up. It will automatically take and break up the hydrogens. How many hydrogens joins to an ammonia, the nitrogen molecule, the nitrogen atom? 3. So how many hydrogens will disappear from here? 3 molecules. So what is left over in the reaction? 2 atoms that's joined together like that, and 3 more hydrogens that are joined together like that. Okay. Let's say this is the situation where equilibrium is reached. Will the reaction stop?
Because it's spontaneous.
Will the reaction stop there? No. And in the end, a dynamic equilibrium is reached. What does it mean?
The reaction will not stop.
So I'm trying to visualize it, but my visualization is not an animation. So the reaction won't stop. You see, this reaction will carry on. Those nitrogens will break up to form ammonias. But those ammonias that were formed, they will break up to form hydrogens and a nitrogen. Do you understand now? Okay. So I try to visualize it, but I can't. I mean, the things are static. So, look carefully. I want to draw a rate graph. So this is going to be a rate of reaction graph over time. Okay. I'm going to use a solid line for the forward reaction. A solid line for the forward reaction. So you told me earlier that the reaction starts at a high rate, and as it uses the nitrogen and the hydrogen, the reaction's rate will slow down. Okay? So the reaction rate slows down with time. Are you with me? What is the reverse reaction starting as? Did I have any ammonia initially? So what's the start of the rate of the reverse reaction?
Ammonium.
0.
Yes. And then it becomes
It's
more
there.
gradually.
Ammonia decomposing will start at a 0 rate because I don't have any ammonia.
The reverse. You start from ammonia.
No, you start at a 0 rate. the reverse reaction
No, but I'm
will
saying
start
that
at a
we
zero
started
rate.
with ammonia, and we're reversing it to.
Oh, wait a moment.
You.
You start off with no ammonia. So what will the rate of the reverse reaction be? Nothing.
Then if you're reversing the reaction, you're starting with ammonia.
Okay.
So what you say is that like the graphs of the forward and reverse reactions will be simultaneous. So like you'll start them at the
How do you
same time.
reverse nothing?
Look the way you're saying. Because if you start them at the same time, it means that nitrogen and hydrogen will turn into ammonia quickly first and then slowly. And then at the same time, since the rate of ammonia, there's no ammonia, the ratio is zero. And as there's more ammonia, the rate then will increase in speed and then slow down. And then also,
The more ammonia will decompose faster. So the graph looks like this. Usually on paper, they use a broken line for the reverse reaction. So these two graphs are mirror images of one another. Yes. The forward reaction is the one that will slow down. The reverse reaction is the one that will speed up. Okay?
At the end.
No. In the end, the rate of the forward reaction is the same as the rate of the reverse reaction. So these two lines should be on top of each other now. I want you to notice this is a rate graph. The other graphs we drew earlier today was like a volume against time graph, and the rate will be the tangent of the gradient of the tangent to the graph. So this one, the rate of the forward reaction decreases. Okay? And this one, the rate of the reverse reaction increases.
So why are it the broken lines now?
I'm trying to keep myself sane. I'm trying to visualize the broken line graph and the solid line graph.
rate of the reverse reaction increases.
Okay, but I'm not ready for that, so I cannot. Okay, you're gonna have to. No, it's okay.
I know it's okay. I'm not changing it.
Rate of the reverse reaction. Yeah, P level, right?
Okay. I've drawn a line across from where the two lines are coinciding. That means the rate of the forward reaction is equal to the rate of the reverse reaction. At that point in time where that happens, at that point in time, dynamic chemical equilibrium has been established. If you do anything to change the temperature, the pressure, the concentration of any of the reactants, the system, the chemical reaction system, will react to work against the change. Okay? So I'm going to say it. It's called Le Chatelier's principle. Listen carefully. The way you pronounce it is Le Chatelier. Okay? Obviously, he must have been French. He said, if a system in equilibrium is subjected to changes in temperature, concentration, or pressure, the reaction that will oppose the change will be favored. I'll explain it again in our next lesson. So, a system that is in equilibrium, if it is disturbed, so if there's a change in temperature, concentration, or pressure, the equilibrium position will change in order to oppose the disturbing influence and re-establish equilibrium. Yes, a new equilibrium will be established. Right? So I'll discuss that tomorrow. Please go and spend some time on these concepts so that you can get with it.